This video is all about the second problem for closed systems. Two tanks are connected by a valve. The first tank contains a mass of 2 kilograms of carbon dioxide at 77 degrees Celsius and zero point 0.7 ADM or atmosphere. The other tank or the second tank has 8 kilograms of same gas or carbon dioxide at 27 degrees Celsius and a pressure of 1.2 atmospheres. The valve is opened and gases are allowed to mix while receiving energy by heat transfer from the surroundings. The final equilibrium temperature is 42 degrees Celsius. Now, if we're going to solve for A and B, we're going to use ideal gas model. For letter A, the final equilibrium pressure. For letter B, the heat transfer for the process. And we are given with the specific volume for carbon dioxide is 0.745 kilojoules per kilogram Kelvin. Now let's proceed with the given. Now, if we're going to illustrate it in a diagram, the first tank has a carbon dioxide with a mass of 2 kilograms, a pressure of zero point 0.7 atmosphere, and a temperature of 77 degrees Celsius. The second tank contains the same gas or carbon dioxide with a mass of 8 kilograms, a pressure of 1.2 atmospheres, and its temperature is at 27 degrees Celsius. When the valve was opened, the whole gases from tanks 1 and 2 mixed. Okay? And after a certain time or period of mixing, the final temperature is equal to 42 degrees Celsius. So this is also the equilibrium temperature. CV stands for the specific volume, in this case, carbon dioxide, which is at 0.745 kilojoules per kilogram Kelvin. Now, let's proceed with the solution. For letter A, the final pressure can be found from ideal gas equation of state. So this is already a given equation. For ideal gas equation of state, the final pressure is equal to MF, or the mass of the final mixture, multiplied with R, or the gas constant, multiplied with the final temperature, which is the mixing temperature, all over the volumes of the first gas and the second gas. Okay. If we further simplify this, since we are dealing with two tanks, for the total mass of the mixture, okay, M1 plus M2, M1 stands for the mass of the carbon dioxide at the first tank, and M2, the mass of carbon dioxide at the second tank, multiplied with R, which is the gas constant, times the equilibrium temperature or final temperature or the mixing temperature all over the total volumes of the gases for tanks 1 and 2. Now for tank 1 and 2, we can write the volumes as the following form. For the first tank, V1. V1 now is equal to the mass of the gas at tank 1 times the gas constant times the temperature at the first tank all over the pressure of the gases at the first tank. And for V2 or tank 2, V2 is equal to M2, or the mass of the carbon dioxide at the second tank multiplied with the gas constant R times the temperature at the second tank all over the pressure at the second tank. Thus, the final pressure PF becomes in this form. PF is equal to M1 plus M2 times R all over times TF all over M1 RT1 all over P1. Okay, so this is the expanded form of V1 plus the expanded form of V2 at M2 times R times T2 all over P2. Now, if we're going to factor out the common variables for numerator, which is R, and for the denominator, which is R stands for gas constant. Okay? If we're going to further simplify the whole equations, the gas constants at the numerator and the gas constant R at the denominator cancels out, gives us the following form as M1 plus M2, okay, multiplied with TF all over M1 T1 all over P1 plus M2 T2 all over P2. Now, if we're going to substitute the following variables, PF is equal to 10 kilograms multiplied with the temperature or equilibrium temperature absolute. When we say equilibrium temperature absolute, we're going to convert it to Kelvin or Rankine. For this problem, the degrees Celsius will be converted to Kelvin. So you're going to add whatever values in Celsius with 273 kelvins. Okay. So the mixing temperature, TF, okay, which is at 42 degrees Celsius plus 273 Kelvin gives us 315 Kelvin all over 2 kilograms times the temperature at the first tank at 77 degrees Celsius in Kelvin, that is in 350 all over the pressure at the first tank at 0.7 atmospheres plus the mass of carbon dioxide at the second tank at 8 kilograms multiplied with the temperature at the second tank at 300 Kelvin. Take note, 27 plus 273, that is in 300 kelvins all over 1.2 atmospheres. Now, if we're going to further simplify this, the final pressure for letter A gives us an answer of 1.05 atmospheres. Now, let's proceed with the second problem. The heat transfer can be found from an energy balance. So for internal energy, U is equal to Q plus W. But since both tanks don't exert work, so W is equal to 0. But if we're going to further simplify this, our heat Q now is equal to change in internal energy. If we're going to further expand change in internal energy, it is equal to U F minus UI, or the final internal energy minus initial internal energy. Final internal energy stands for the internal energy after mixing of the gases minus the amount of internal energy prior mixing of the gases when the valve was closed. Now, if we're going to further simplify U1, or the internal energy, or UI, internal energy at the initial state, UI now is equal to M1 times U times T1 plus M2 times U times T2. For the final internal energy, UF is equal to the sum of both masses M1 plus M2 multiplied with the Q times the equilibrium temperature TF. Now, if we're going to substitute U1 or UI and UF to our Q or heat equation, this becomes Q is equal to M1 times UTF minus UTI, okay, plus M2 multiplied with the following quantity as UTF minus UT2. If we're going to further simplify this equation, this gives us Q is equal to M1 Incorporating now our specific volume at 0.745 kilojoule per kilogram Kelvin. So M1 CV times TF minus T1 plus M2 times CV times the following quantity as TF minus T2. If we're going to substitute now the following variables, for M1, this is the mass of the carbon dioxide at the first tank at 2 kilograms times our specific volume for carbon dioxide at 0.745 kilojoule per kilogram Kelvin multiplied with TF, or the equilibrium temperature after mixing at 42 degrees Celsius converted to Kelvin, that is in 315 Kelvin, minus the temperature at our first tank at 77 degrees Celsius, or in Kelvin, that is in 350 Kelvins, plus M2. M2 stands for the mass of carbon dioxide at the second tank at 8 kilograms, multiplied with our specific volume at 0.745 kilojoule per kilogram Kelvin, multiplied with the following quantity, TF minus T2. TF, it is again our final temperature or mixing temperature at 42 degrees Celsius converted to Kelvin, that is equal to 315 Kelvins minus 300 Kelvin. This is the temperature of the gases at the second tank at 27 degrees Celsius converted to Kelvin. Now, if we further simplify the following quantities, okay, with proper inputs at your scientific calculators, this gives us our final answer for this problem. The heat now is equal to 37.25 kilojoules. Now that ends my video presentation for this problem. Our next video will tackle about open system calculations.